Section 2, Chapter 3. So 3.2, Measures of Variation. We just got done doing measures of central tendency, which talk about the middle number. Measures of variations are numbers that talk about the spread of the data. Your most basic measure of variation is your range. It's taking the largest number and taking away the smallest number. The only problem is that this is very greatly affected by extreme data values. So if I've got one number that's extremely big or extremely small, I can get a very wide range when most of the numbers aren't even separated by maybe one or two values. Okay. It's really easy to compute though. Like for example, I've got 10, 13, 17, and 17, and then 18. I'm just going to take 18 minus that 10 and get a range of 8. So the range between the highest and lowest is 8 values. And like I said, easy to compute, but really sporadic. Standard deviation is your better way of measuring variance. Okay. In fact, variance and standard deviation are very closely related. They both measure the spread of the distribution around the mean, okay, the center. And the formula to calculate the standard deviation and variance are slightly different than we're dealing with population and sample. I'll start talking about sample right away because most of the stuff we'll deal with is sample. So both of these are going to be the sample variables and sample, what I want to say, notation. Like for example, yesterday we talked about the little n being the sample size. And we talked about x bar being the sample mean. So if you're working with sample variance and sample standard deviation, you're using those two values. Okay? We'll talk a little bit about how to use these and whatnot. You'll see this in the book, in the back, or in the formula sheet that I'll give you to. The relationship, if you see, is just a difference of squaring. So if I've got my standard deviation s, I can square that number to get my variance. Calculating sample standard deviation. I go through a process here. First of all, you do the mean. So take the sample, calculate out what that average would be. Subtract the mean from each data value, and that's going to look like in the formula x minus x bar. So if you were to see that, it means to take the sample mean from each individual data that you've got, square each of these terms. So you'll see x minus x bar, and then after that, there's a square on the outside. To sum them up, remember, sum is the uppercase sigma. Okay, and all that. Then you're going to divide by the value of n minus 1. And then at the very end, to get all that, take the square root of that value, and there is your sample standard deviation. So I'm going to take a small set of, I believe it's 5 or 6 numbers. That looks like it's 6 numbers. I'm just going to walk you through the process of all these numbers came about and where they came from and whatnot. The mean. Okay? So these are my numbers. I got a 2 in there. There was a 2. There was a 3, a 3, an 8, a 10, a 10. Add them up and you get 36 divided by the 6 numbers there are, and you get a sample mean of 6. So you will see this sample mean of 6 different times because you have 6 pieces of numbers. So the x value of 2 minus 6 gives you negative 4. 3 minus 6 gives you negative 3. 3 negative 6 gives you negative 3, and so on. Notice that you have some negative numbers. You could possibly get 0. You could get positive numbers. That's fine. The next thing, though, is to take this number and square it. Careful on your graphing calculator, because negative 4 to the second power, if you don't type it in right, we get to negative 16, but negative being squared is always positive. So you get 16, 9, 9, 4, 16, 16. Add all those up, and you end up with 7. Okay. So to take my 70 divided by 6 minus 1, 5, I'll get a sample variance of 14. If I take the square root of that number, I get a sample standard deviation of 3.7. Now, what does that mean? We'll talk about that a little bit more, but in relationship to your average of 6, 3.7 is considered, your bigger, small, or whatnot. Talk about the spread of the data. Okay, just another one to work through. Just 3 sets of numbers. So if you want to kind of walk your way through it, talk through this one as well. You got 30, 20, 22, add them up, and you get 78. Divide that by 3, you end up with 26. So to get three numbers, take away that average of 26, take away 26, take away 26, and that leads you to the positive 4, 0, and negative 4. Some of these is 0, but you don't want to add them up right now anyways. You want to square them to get 16, 0, 16, add them up, and there's your 32. That's the number that you're going to use right here on the numerator. And we're talking about 3 numbers, so 3 minus 1 is 2. So 3 divided by 2 is 16. Your sample variance is 16. Take the square root of both sides, and you get a standard deviation of 4. Okay. Again, what does that mean? Well, 4 has to be in relationship to the average that we got from 4, which was 26. I say 4 is pretty close to 26, at least closer than the other 2 were. So I would say that these data is pretty close together. There is the computational formula that you can use as well. It's got some different notation. This one's got the sum of x squareds and the parentheses around the sum of x and then the square. They're different. The sum of x squared, this means take x and square it, okay, then add them up. The parentheses and sum of x squared means to add them up, the values up. Then here we go, square. So that's the difference between the two. It's another way, and really, actually, it's going to turn into you're going to show me how to do this by hand, maybe on one problem, and then after that, I'm going to show you how to use technology to compute these. Anyways, if we did these all by hand, we wouldn't get to a lot of the different stuff, just because you'd be spending a lot of time plugging and chugging your calculator. But just for the sake of showing you how this other formula works, I took my x values of 4, 5, 5, 7, and 4. I add them up. There's my sum of x, 25. Took all of those, 4 to the second power is 16, 5 to the second power is 25. Add them up, and that's my sum of my x squared. So when it comes to the computational formula, those are really the only 2 numbers I need, along with how many numbers are in my set. So since I'm looking at 5 numbers, whenever I see I think I've got it all worked out. Nope, I don't. So let's go back here for a second. There we go. So the sum of x squareds right here would be the 131. This is actually a fraction right here. The way the book writes it is very similar to that up there. I like to write it like this. It's going to be 25 squared over 5 all over 4, and then take the square root. So I do the fraction of 25 to the second power divided by 5. I got 125 right there. 131 minus 125. So 131 minus 125 divided by 4. And then take the square root. So that leaves me with 6 over 4, and then take the square root. So 6 divided by 4, 1.5. The square root of 1.5, get a standard deviation of 1.2. Okay. There formulas in the back of the book. They're for population standard deviation. Again, we deal with samples more than population, but really mean, nothing changes. Yeah, you'll see a different looking variable for mu and a capital N. That just means number of objects again. Just a little different way of looking at it. Oh, I meant to get rid of this stuff, guys. Sorry. So what you've got now here, though, for variance and standard deviation, though, is you've got the lowercase sigma. That just means that it's population variance or sample variance. And look, if you're doing population standard deviation, you're going to use the population mean and the population sample size. The big thing to note is there's no -1 at the bottom. So you'll probably see a formula in the back that's more like this. The sum of x minus mu squared all over n. Okay. Again, where n is the same thing as little n, just kind of semantics because you're working with population. I'll show you that how your calculator will spit this one out too, and you're not going through and working with it by hand again and again and again. Okay, the coefficient of variation. It is difficult to compute the standard deviation from different populations because there's many different units of measurement. I think of it this way: if we were to do a study on temperature in the United States, we'd do that by Fahrenheit. If we were to go anywhere else, it's basically going to be Celsius. The coefficient of variance will give you a percentage that will let you compare the two findings without having to worry about, hey, this one's like in Fahrenheit and their temperatures are way higher than the ones in Celsius. The coefficient of variance expresses the standard deviation as a percent of the mean. Okay, the coefficient of variation is unit free. There is a good comparison between populations or samples. Like temperature-wise, there is no degrees Fahrenheit when you get down with the coefficient of variation because it's unit free. For population and sample, it's just basically semantics with the letters. S for sample standard deviation, sigma for population standard deviation, mean and mean. So you're going to take whatever standard deviation that you came up with, and you're going to divide it by the mean. Now, the reason why you're multiplying by 100 is this is a percentage. You're taking an S1, making a percentage. Okay, use the coefficient of variation, how to compare those two numbers. Well, which numbers are more consistent to help deal with, and which one's more variable. So this means spread out if they're variable. Got a slight comparison here. So it says we got a sample of newborn infants that has a mean weight. Okay, so a mean weight, it comes from a sample, so that's x bar, and a standard deviation S of 1 pound. Okay. We're going to compare that to a sample mean of a 3-month-old, which is different than a newborn, okay, that has a mean weight of 10.5 and a standard deviation, sample standard deviation of 1.5. Which is, between the newborns and 3-month-olds, more variable in their weight, or which one's more like scattered than the other. So we'll take the 1 over 6.2 times 100, and we'll take the 1.5 over the 10.5 times 100. Okay, so standard deviation over the mean, standard deviation over the mean. So 1 divided by 6.2 times 100, I get 16.12%. Okay, 1.5 divided by 10.5, okay, I get that as 14.2%. Since 16.12 is higher, that's the sporadic one. So you would say that infants have more variability. Not by a whole lot, only out by 2%. Now, it is possible for you to get a percentage here that's bigger than 100%. And if that were the case, that means that your standard deviation is so much bigger than the mean, your data is all over the place. Okay, standard deviation is basically like this. The smaller your standard deviation, the closer that number is to 0, the less crazy those numbers are. Okay. Chebyshev's theorem. For any set data that has k number of standard deviations, it's got to be greater than 1. You have the following expressions or percentages because of this expression. Now, if it's at least 2 standard deviations away, I'll put a 2 in for k, simplify that out, and I get 3/4, which is 75%. So what that means is on a number line, you've got your average. If I were to add 2 standard deviations to that average and subtract 2 standard deviations away from that average, I'm going to end up with 2 numbers, right? A upper number and a lower number that will give me at least 75% of the original data. If it's at least 3 standard deviations away, now I'm plugging in a 3/4k, and that's going to give me 8/9 or 88.9% of the data. And now on my number line, I'm going to start with my average, but now I'm going to go a little bit farther. I'm going to go 3 standard deviations away on both directions, and now I've got 2 numbers that all the data, or not all, but 88.9% of the data should lie. Okay, at least 4 standard deviations away is 93.8, and it makes sense, right? That means that you've got your middle mean. You're now going to go plus 4 of those, and you're going to go down 4 of those from the mean. But the important thing about this is you need to know what the average is and what the standard deviation is to come up with these intervals. And you are coming up with an interval. You're coming up with a low number and a high number. Okay, so it says mathematics class completes an examination that it's found that the mean is 77 and the standard deviation is 6. Chances are this is a sample. It really doesn't matter, but we'll say sample mean is 77, sample standard deviation is 6. Okay, we want at least 75% of the data. Okay, so going back, what value would go in for k that gives us 3/4 or 0.75? Well, that k value would have been 2. So to come up with our interval, we'll take our mean of 77, our standard deviation of 6, and we're going to add that number and subtract that number to get 65 to 89. That means that 75% of the test scores were between 65 and 89. If you put a little caveat to it of at least, it could actually be more than that. I know I went fairly fast. There was a lot of information here. Again, remember, you can always stop this. Maybe you want to print out the note sheet to kind of follow along with this too. But my idea is that you go through, try at least a couple of these problems, and we'll practice standard deviation by hand, and we'll do Chebyshev's theorem in class rather than you doing it on your own.